Can we, you said in classes, the take home is due the 3rd or the subsequent, the 10th? When it's due 3rd for now, and then if we.
It'll be the 10th. Yeah, it'll be the 10th.
I was saying she knows she's going to be done before the 10th anyway. I don't know why she did.
Everybody.
That's for people like me, but me.
So questions from the homework, ANOVA? William?
A simple question I may have missed. I know when we talk about like ANOVA one way, you have to have 3 factors at least. You can't have like a dichotomous variable because you use a t-test. I was wondering if you're doing a 2-way ANOVA, can you have a 2x2 in that case, or do you have to have a 3x2?
No, if you had 2x2 ANOVA and you wanted to test the 2 main effects and the interaction,
Okay.
it would make sense to do the ANOVA.
Okay.
And even if you didn't want to test the interaction, which we always test the interaction, but if for some reason you didn't want to, it would still make sense just to do the ANOVA.
Okay. That's what I thought, but I just wasn't sure if you had to have those 3 or more levels on one of the variables.
Nope. And you could actually run a one-way ANOVA with 2 groups, and it doesn't know the difference. It will give you output, and the output would be the same. You'd come to the same conclusion as you'd come if you did a t-test. If you went to publish that, somebody might look at you and say, "Why are you doing ANOVA? You could do t-test, or you should do t-test." Good question. Other questions about homework? Is that 5? Is that homework 5 that you just submitted? One more left, yeah? Other questions about homework 5? No? So the good news, and maybe bad news, is that we're going to talk about analysis of covariance and MANOVA today. And we're going to review a lot of the same material because this is exactly the same framework. We just added in some features that we want to covariate out of our analysis. And MANOVA, as you'll see, exactly the same after we get past the first couple steps. Exactly the same analysis, exactly the same interpretation. So you'll have to apply that same logic that you applied to your data to a couple more cases over the class period today. So there'll be plenty of opportunities for us to review. So I want to start with analysis of covariance, and just a continuation. I believe this is exactly where we left off last week. And so analysis of covariance is used to test for main and interaction effects while controlling for the effects of selected other variables or covariates. It can be a single one-way ANCOVA, or it can be a multi-factor ANCOVA where we'd have 2 or more independent variables. ANCOVA can increase the sensitivity of the test by reducing the error term or the within group variation if you think about sums of squares and the within group sums of squares. Not the between groups, which is the good sums of squares. This would be the bad sums of squares because it's the within group, within each of your groups, that variation. We can reduce that. But it comes at a cost, and it can, in some cases, depending on the set of covariates in the situation, also reduce the between group variation. So as has been the case throughout, there's a price to be paid for most everything we do, and the potential price you pay for reducing your error variance is to also reduce potentially even more your between group variation. ANCOVA can be viewed as asking, what if all cases score equally on your set of covariates? So you determine what you want to covary out of your analysis, and that's normally determined based on theory. What do you want to, theoretically, what do I need to remove from the analysis so I can have more confidence in the results? And that would be sort of the first step. And then you can view that as really asking the question, what would the analysis be like if all of my participants scored equally on whatever that set of covariates are, or that covariate, if in case of a single covariate, that covariate is, which is a powerful. It's a powerful analysis. It's useful in many situations to be able to make that argument. And we'll talk a little bit about that as we move forward in terms of some of the issues that arise when we do that. So this is the data that we used at the end of class last week, where our dependent variable was how much the individual trust our media. And so this is a sample of US citizens for the most part, and one of the questions was how much do you trust the news media? And some scale, I haven't looked at it, so I'm not sure, but probably 1 to 7. 1 meaning I don't trust them at all, 7 meaning I have a great deal of trust in them. And so we have trust in the media, and then we had 2 independent variables. One was their party identification, Democrat, Independent, and Republican, remember? And then the other was, were they male or female? And so that's the analysis that we did last week. And maybe we want to examine the same two-way ANOVA, but we want to add what I would see as theoretically meaningful covariates. Maybe we want to covary out or take out the impact of age. Maybe we want to covary out education. So set everybody's education to the same level as one way you can think about that. Or covary out levels of education. So this would allow us, somebody could come to me and say, well, yeah, sure, Democrats trust the media more than Republicans, but maybe it has something to do with the fact that, and I don't think this is true, but somebody could say this, that Democrats have higher levels of education on average than Republicans, and I would be able to say, well, I've covaried out education, so that argument, while would make sense in some contexts, doesn't apply in this context because I've held constant, statistically anyway, I've held constant people's levels of education, how interested they were in a particular campaign, high levels of interest, very motivated to seek out information, low levels of interest, uninterested, how much attention they spend on, when they do watch news or consume news, read news, how much attention do they pay to it, or is it just sort of in the background and it's something they don't process very carefully? Do they tend to be, how much pessimism do they have? Something else we covariate, how much they talk to family, friends, or coworkers about politics. So these would all be, I can make an argument theoretically based on past research for sure, that these would all be meaningful factors to, or covariates to exclude from this trust in the media analysis. And then we'd be able to look at the impact of party identification on media after holding constant all of the set of covariates that I have listed here.
Does this one get used more?
I can answer that. That would be a question that if we could, again, get a whole bunch of journal articles, and I think analysis of covariance, my instinct or my first reaction is it probably gets used less than analysis of variance. But that's just a guess. I think they both clearly get used a fair amount. Yeah, good question. Anybody else have a sense?
So an ANCOVA is a lot like ANOVA in the addition that it now can provide the same insight but control for variables that we might not necessarily want to have a great deal of insight, but we want to control for their fluctuation.
That's right.
Okay.
That's right. That's well put. And does that make sense to everybody? That's exactly what we're hoping to accomplish by removing the influence of essentially what we're doing is we look at the relationship between age and trust in the media, and we take out whatever that relationship is. We set that relationship to be zero, and you'll see in a minute it's set to zero. Is there a relationship between trust in the media and education? And to the extent there is, we use math to partial that relationship out of the trust in the media variable. Chris?
What kind of limitations do you have in terms of how you collect your covariance, right? So I can collect age, like, are you over 18? Yes or no, right? That doesn't seem to be useful, but is it possible to use those?
Sure, it would be anything in somewhere probably next screen. The same constraints. Treat them like independent variables in a regression. They could be dichotomies or continuous covariates. If they're nominal, you have to dummy code. They can be nominal, but you'll need to dummy code them. And so think of covariates, and they have to meet that same criteria as the independent variables in your regression analysis. Did that get your question? So yeah, I think that probably could be useful. Potentially could be a useful correlation or covariate in almost every case. To have more than just teen or not teen probably would be better than, right? To have actual age probably would be better, but it might be better than not having anything.
I was just going to say, and I think to back up to Fidel also mentioned that education psychology uses a lot of ANCOVA because they want to say it's the teacher or they want to say it's the age or.
Yeah.
That's what I was thinking. Like, that's where my question came from, like, thinking this would be most useful because then it just kind of proves your point more. Like, I don't see why you wouldn't.
I wouldn't use the word prove,
Well,
but
yeah,
you have a
not
stronger
prove, but
argument.
like,
You have a
yeah.
stronger argument. Potentially, and so somewhere I give a few details about that. For example, if you do a really good experimental study where you have the ability to randomly assign people to conditions, if it's well designed and nothing goes wrong, there's no need to have covariates. I cannot think of a reason to have covariates because you've randomly assigned people to your conditions, and if random assignment has worked, which sometimes it doesn't work, right? Sometimes we flip a coin and we get 10 heads in a row, right? So sometimes if you randomly assign people to groups, you might get all of the people of one kind or a large number of the people of one kind in one of your conditions, and if that's the case, then that might be something that you might have to go. But in 9,999 out of 10,000 cases, random assignment works, and so we have confidence that our groups are equal on our dependent variable prior to our manipulation of independent variables. So there's no need to do this. I used to have some good arguments with Professor Pfau. Those of you that, a few of you maybe met him, Michael, when he was still with us, was the chair of the department, hired me, good mentor, friend, but we'd have some, because he just habitually read any of his inoculation studies, and he would do MANOVA with about 15 covariates, and there was never made any sense why. Well, 15 is an exaggeration. Let's say 5. 5 covariates, and it never made any sense why he did that. He never made a good argument for we covaried for these things, and it always came off to me as he was like on a fishing expedition. Let me add he may or may not have been. I never did research with him in that way. But it comes off to me as a fishing expedition because, well, let me just try adding covariates into my analysis until I get some results that I'm happy with, and then I'm going to publish that. And he had the ability to write and the name in the field where just about anything he wrote, he got published. And so I'd have arguments. I wouldn't be quite that blunt about it, but I did. I've made it pretty clear that it just doesn't seem right to me that you don't make an argument for why you are parsing out some of these features, and he never relented or gave in a bit. He said it. Who knows what he said, but William.
What if you're not doing that way, but working backwards and using ANOVA first, and you find significant effects, but you want to like preempt arguments, maybe that it's education or something else? Then you could use ANCOVA as like a secondary test to see if your significance still functions.
I mean, if you have reason to believe that education isn't, and you're talking about experimental research, I assume, not survey research.
No, I'm talking about cross-sectional.
Oh, cross-sectional, totally different story. Yeah, if you're doing cross-sectional research, then I think that, like this data is, then the need for covariates, a totally different ballgame. But for survey research, where you collect data at one point in time, cross-sectional, then I think using covariates makes perfect sense. Have to make an argument for the inclusion, and I think the point that you're making, William, would be an easy way to make that argument where you could do your analysis without the covariates. You could preempt potential counter arguments to the claims that you're making or the hypotheses that you found confirmation to, assuming by maybe redoing the analysis with a few covariates, and that would surely strengthen your ability to persuade more than it would lessen it. Again, from my perspective, assuming you have some reasonable argument for why you're including what you're including, and it's just not it doesn't come off as just a data mining exercise that you're just worked with a bunch of variables until you found something that you liked. Tyler, did you have your?
Yeah, so just to make sure, this works when you add covariance into your model, it works the same way as a regression where you limit the degrees of freedom with each inclusion.
That's right.
And then the more you should use that adjusted R squared to account for that limited degrees of freedom. That's one of the prices you pay for adding covariance is it does change your degrees of freedom. I'm not quite sure I follow you in terms of the adjusted R square. I might have them wrong.
We tend to use, in this context, we'd probably use eta square or partial eta square.
Right, beta, sorry. No, not adjusted, but eta and.
Yeah, and partial eta square is not the same as adjusted R square. They're two different variations on an effect size for eta and R. So, but the answer to your first question is absolutely yeah. Did somebody else have Pavitra?
Yeah, because you mentioned inclusion criteria, and I mean what if there's 2 or 3 covariates that sort of justify that inclusion criteria, but then now we have a concern with we've had too many covariates. How do we sort of balance it, or is there no concern with adjusting for a whole bunch of covariates?
I think there'd probably be limits on what you probably wouldn't want to have more covariates at the one extreme, more covariates than you have n. So that's not very helpful. But there'd be some limit below that would be. But I think as long as you make a reasonable argument for including the covariates, and cite past research as finding them to be significant influences or theory, then I think the upper limits are probably fairly high. 20 probably be pretty high. I think it'd probably draw some attention, but 5 or 8 probably wouldn't draw too much attention. I wouldn't think. Good, good. Other comments, questions? And so the researcher then would be able to argue that the results are based on holding the set of covariates constant, e.g., controlling for those features. And then the final point there is, what are the criteria for making a causal argument?
X precedes Y.
X precedes Y. How many criteria are there for the 3? So X precedes Y, that's 1.
No Z variable.
What's that?
No Z variable causes Y.
And we call it spurious. Spuriousness would be no spurious relationships, and then the third would be X and Y are correlated. And this really doesn't get us down the path any further in terms of making the causal argument, because with just the ANOVA, we might be able to show that X and Y are correlated, right? That there's a relationship there between the independent variable and the dependent variable. I guess potentially the covariates could work towards reducing somebody's suspicion that your relationship is spurious, that there's some third variable, some Z variable, as William said, some Z variable that's causing the relationship between that, that's causing that Z variable that's related to your to both of your variables, which is causing the X and Y to look like they're correlated when in fact it's just as spurious. So potentially you'd be able to move in that direction. I don't think it gets us any closer to being able to say that X comes in time before Y, that the cause comes before the effect. I just don't think there'd be a set of covariates. There'd be a set of covariates that you might be able to use that you might be able to make a slightly more persuasive argument. I would never use the word causal, though. I think you're only studying, and if I have not said this before, I don't know that I would ever use the word causal. Just because it's just such a hot button. Some people feel strongly about it, and we never have certain evidence for causality. Even with the best experiment that you can possibly design, spent $100 million or whatever your budget is, and you designed an experimental study, you're still doing hypothesis tests using probabilities, right? And even if your probability of making a type 1 error is 0.0001, it's still not 0, and so you can never say you've proved causality. There will always be some element of doubt there. So I would just be careful about using covariates to bolster the argument that you have a causal relationship, particularly with cross-sectional or survey data. So you can have one or more covariates. Covariates can be interval or dummy coded categorical variables. And really, I should say interval ratio. Same as we have for independent variables for regression, right? And if we want to think abstractly a little bit about how does the procedure remove or partial out the relationship between the covariates and the dependent variable? How is that removed? It's removed by first regressing the dependent variable on the covariates, and then running the ANOVA on the residuals. And remember what a residual from regression? This is a good question. Remember what residuals are? What's a residual?
Predicted minus,
What is it?
predicted minus the real one.
Yeah, your actual value minus your predicted value would be the residual or the error. Or that would be the predicted minus actual minus predicted would be the residual. Right. So actual minus the predicted would be the residual. And so in this case, the residual would be after we've removed all of the impact of our covariates. Let's run the ANOVA where the residual here would be your dependent variable. And you could, I've actually done this in some cases for research where, for whatever reason, I don't remember what but I've seen others do it as well, where we weren't able to do analysis of covariance. And so what we did do is we did regression, calculated the residual, and then used the residual as the dependent variable. And the results end up being the same as if you did analysis of covariance. And this will allow us to see if any of the independent variables or factors are still significantly related to the dependent variable after removing the variation due to the covariance, because the residual would be that after we have removed the impact. And so just to give you, hopefully you have this chart in front of you. It becomes difficult to see from where you're at, but this is our data, and I just did an analysis, and I told SPSS to save the unstandardized residual for me, which is what this column is. And so I had trust in the media as the dependent variable. I had age, education, campaign interest, attention to news, pessimism, discuss politics, all as independent variables in the regression. Ran the analysis, but before I ran it, there's a little box in regression that says save. And one of the things that you can save is unstandardized residual. We saved some other things there in the past. I don't know that we've ever worked with unstandardized residual. You could do standardized residual and it would just have mean 0 standard deviation when I just did unstandardized. So it's in the same metric as the original trust in the media. And we can see, so the correlation between age and trust in the media is really small. It's 0.01, really small. How old, with this data anyway, older or younger does not seem to be influential factor with how much trust somebody has in the media. And so this is age with trust in the media is 0.011, and age with being correlated with the unstandardized residual is exactly 0. So the residual removed all of the relationship, wherever there was a relationship between age and trust in the media, it removed that on the unstandardized residual, because here we have a relationship, and then looking at the unstandardized residual, the relationship is exactly, there's no relationship. The relationship is 0 out to 1,000 decimal places. Here's another one. This one is significant. So as education increases, people trust the media less. Look what you do. As education increases, trust in the media decreases. And the correlation is minus 0.151. Not surprising. But what is sort of amazing to me is that with the unstandardized residual, that correlation with that same feature, education, is now exactly 0. And so it removed all of the covariance between education and somebody's ability to trust in the media. And so what we're doing with analysis of covariance is this becomes our dependent variable. And it seems like, yeah, this is utterly unrelated to all of our covariates now, right? Because the relationship for all of those is exactly 0. And so our new trust in the media variable, again, is utterly unrelated to all of our covariates. And I say utterly unrelated because each of these are exactly 0. And so if we run the ANOVA on this new trust in the media variable, clearly we'd be able to say this is the relationship between our independent variables and trust in the media after we've removed the influence of our covariates. And so we're not getting into the math so much of how that happens, although it's fairly straightforward, and it's all work that we've done in the past. We calculated residuals in the past, where we took the actual value, and you had to do this for homework. You'll have to do it for the take-home exam. Actual value minus the predicted value, and that would be the residual. And so it's just doing that. It's just doing that same process, creating a new variable that we're calling in this case just unstandardized residual, and then running the ANOVA on that new variable. Does that make sense? And so just to have it somewhere, I think you guys are all probably more expert at SPSS at this point than I probably am. But just to we'll run the ANCOVA that I've sort of demonstrated, and then we'll look at the results, and that should be in the couple pages of your the next couple pages of the slides. And so we're going to do again general linear model, univariate, and our trust in the media is going to be our dependent variable. Fixed factor is going to be whether they're male or female and their party ID. And then the rest of these variables are all going to be covariates. And so you guys would have been able to figure that all on your own. And then you could ask for the same set of statistics that we have in the past. In this case, we might ask for one thing that see here, post hoc is not grayed out, and so I can click on post hoc and I could slide over any of these post hoc tests or any of these variables, and then select. I could slide over female, and I could select the post hoc test that I want to do for that. But when I add the covariates to the analysis, our post hoc button is grayed out. And so we have to get the post hoc test a different way. You probably would be able to do Bonferroni test all by yourself without requesting them. But what we do is under options. This is one way to do it. Do we need post hoc test for female?
No.
Because it's male or female. And why not?
Because it's 2 levels.
And so what do I do? It's 2 levels.
I can do a t-test, But then, I mean, I know which ones, if I see the means, I could say which one, if the test is significant, I would know which one is the.
Exactly. Just look at the means. You have two. If it's significant, if that main effect is significant, just look at those two means, and you'd be able to tell is male higher than female or female higher than male. So there's no. And in fact, I think SPSS would give us a warning if we did try to do that. And so we're going to say display means for, and we can say compare main effects here. And least significant difference is the same as we did no adjustment. Or we could do bond for only or the SIDAC. And you would just click whatever your preferences are. And we could do that. And we could say, give me the descriptive statistics. I want effect sizes. I want the homogeneity test. What else do we ask for there? I think that's it. Plots. We might want to do female and PID, and I always just do both of them. Contrast, I never used this contrast. If you want to study it, there might be some. I've never used it. There might be some situations where it's handy. And just sort of FYI, this is under model. And this will be something that we'll never have to use in this class, but just so you have a fuller sense of what the potentials are here. We're saying I want to do the full factorial, which means we're going to get a main effect for party ID, a main effect for sex, and then the interaction between those two. Let's say for some reason I didn't want the interaction. I don't know why you'd want that, but in some cases you're just interested in looking at the two main effects. You'd be able to do a custom model, and you could say I want to do main effects, and you could just pull over that, and you could pull over that. And that would be your custom model, and you would just get two main effects. You wouldn't get the interaction. There's probably not a lot of situations where that would apply, but I could see it applying. Maybe theoretically, there's no reason to think that there's going to be an interaction. So why burn that degree of freedom for that extra? And you'd be able to easily, you could do that easy enough. And then the only other thing, so that's just sort of FYI, as you continue to do social science, it might be something that will be of use. One of the other things, and if you want to go down a rabbit hole, start to study different kinds of sums of squares. So we always use type 3 sums of squares, but it's as big of an argument as you can find in the social sciences, whether you should use type 1, type 2, type 3, or type 4 sums of squares. I think the big argument is between type 3 and type 2. And so it has to do with how variables are entered into the analysis. But by default, SPSS does type 3 sums of squares. But there's books written on this topic. If you take an ANOVA class, you'd probably study and learn a fair amount about each of the 4 types of sums of squares. I don't use ANOVA on a regular enough basis where I even remember the difference between 1, 2, and 3. Although I do remember that I think type 1 sums of squares is you enter the variables into the model in a very specific order, because that's the order that they'll be entered into your analysis. With type 3, they're all entered in at the same time. With type 1 or 2, I forget, each variable is entered in one at a time, and you just end up having a much different analysis than if you entered them all in at the same time. At the end of the day, you get a similar analysis, but getting there is a much different process. So that's the place where you change that rule of thumb. Unless you know exactly what you're doing, you should never change that. Nathan?
Is that like the blocks and hierarchical progression?
It's similar, but to be honest, I'm not. Yeah, you say that, and but in hierarchical regression, you would add, let's say you have 4 variables in your first block, you'd add those in a block, and you could sort of examine the impact of those 4 variables on your DV. And then maybe you add in another 4 variables in a second block. But that second block, you're not looking at it in isolation, you're looking at it along with the first 4, right? Yeah, and so I think it would be similar, but in this case, under the auspices of ANOVA framework or generalized linear model instead of regression, because but there's probably some differences there, subtle or otherwise, that I'm just not familiar with. But again, good question, and it's sort of beyond the sort of my working knowledge of. I think your textbook has some good information about it, and again, you can find some decent information in other places about sums of squares. So where does that leave us? We're going to still do full factorial, and I'm going to say okay, and this is my analysis, and I think what I gave you on the next slides that we have will be very similar to what I just ran. There might be some nuanced differences, but they should just be that. So I guess a few more background or sort of assumptions. ANCOVA, just like regression, is sensitive to multicollinarity. If somebody on your committee asks you to define multicollinarity for them in your defense of your general exams, what would you say? Yeah. Independent variables highly correlated. How high is too high?
0.7.
Yeah, it depends, but 0.7 is a decent rule of thumb. So, yep, and so multicollinarity is something that we've talked about a fair amount in this class. If you have highly correlated independent variables, you might be better off just deleting, probably greater than 0.7. You probably should just remove one of them to eliminate any potential problems associated with multicollinarity. Here's my mentor, Professor Pfau, habitually using covariates in his experimental designs. Since we randomize experimental research, in principle, we fully, we have control for all of those things by the random assignment. Our group should be not significantly different on our dependent variable if we divide them up by groups. Will they be exactly the same? Will they have exactly the same value before we manipulate the independent variable? No, because by chance you wouldn't expect them to be exactly the same. But would we expect them to be significantly different? Absolutely not. Unless somehow you had a streak of bad luck or you didn't do your random assignment very good. You did something where everybody that came in at 8 in the morning was in one of your conditions, and everybody that came in at 8 at night, God, that'd be bad design. Everybody that came in 8 at night would be in the other random condition. And somehow you flipped a coin to determine that. And that would just be bad design. And you then would have problems that we probably wouldn't be able to fix with covariates. And so, of course, if randomization is a concern with your experiment, you could then potentially add some covariates to strengthen your analysis. So let's say we're doing we're studying K through 12 education, or something similar to that, and we're using textbook. We're studying a new form of a textbook, and of course you can't do. And we're working in a school district. You wouldn't be able to go in one classroom and randomly assign, well, this student is going to have this version of textbook, and this student is going to have another version. Random assignment wouldn't work in that way, but you'd be able to potentially randomly assign the school. which is less than perfect and could cause some problems, particularly if there's some differences across schools, and I bet there usually are. And to the extent that there are differences, you might be able to add some covariates to your design to strengthen your experiment, to say that, well, maybe the socioeconomic status of those kids or the students in one school is higher or lower than some of the other schools, and you might know that information, and you could covary that information out of your analysis, or there might be some other variables that you could think to covariate out. So that would be for me the argument that makes the most sense for I'm going to use covariates for my experiment because something happened with the random assignment. It just didn't work. I wasn't able to do it well because of particular constraints that you might have as part of your study. And I would say the goal is to have as few covariates as possible and have them all highly correlated with the dependent variable and, to the extent possible, uncorrelated with each other. To have a bunch of highly correlated independent variables that are uncorrelated with your dependent variable. So correlated with each other, but not correlated with your dependent variable is not a good situation because there's nothing you're going to there's nothing to partial out. So the idea would be to have variables that are correlated with your dependent variable and tend to be uncorrelated with each other. And so this should be close to the results that you have, and just sort of to take you through what we have. We can look at the relationship between the covariate and the dependent variable by just examining the F test that's associated with each of our covariates. And so, for example, age, the F value is 0.265. The significance level is 0.61. And the effect size, rounds to 0 at 3 decimal places. And so, as we saw earlier, there's not much of a relationship between age and whether somebody trusts the median or not. And that's also exemplified here. Education, on the other hand, there is a meaningful relationship. And we can see that because our F is 25.8. P is less than 0.001. Would we say P is equal to 0? And that's, why not? Yeah, there's a 1 or there's some number at the end of that somewhere. So if you learn nothing else from this class, just don't do that ever. And I'll feel like I've had some small contribution to your and I used to, as a student, I was the paper pusher for Bill Benoit, who was the editor of Journal of Communication at the time, and so I read a lot of reviews as a student, and it's a great experience. And people just, and that's probably where I picked up on it, is somebody would make the claim that the P is equal to 0.000, and people sort of come unhinged at people making those kinds of claims. And so I nearly come unhinged when I see that. For me, it indicates, I don't know, maybe not being very careful or not understanding one of the two. And I would hope that neither of those are the case when you're doing research. And so we can go and we can look at the rest, and I highlighted the other two covariates that were significant. And for the most part, in this analysis, we really don't care that much about our covariates. We probably, if I were writing this up, I'd have one sentence that would say, education, news, and pessimism were significant covariates, and I might somehow try to jam in an F test or 3 F tests and p-values for all of those in that same sentence, and it'd probably be sort of clunky looking. And then I would also say that age, interest in politics, how much they talk to people about, how much they talk to people about politics were not significant, and I probably would not give the F test because the F tests are all pretty close to 0 and they're all non-significant. So this is probably, I'd probably give this first, just a quick sentence, maybe 2 at the most, assessment of the covariates, and then I would go on to talk about the 2 main effects and the interaction. Brittany, do you have questions?
I was just wondering, so I know like R squared is the effect size, right? And now we're on the like partial eta squared. Does it still follow the same small, medium, large numbers that we use for R?
Yeah, I would use the same. So small is, what's small again, everybody? This will be on the test.
0.01.
This is fair to be on the test because we've gone through this how many times?
0.01.
0.01.
0.09. 0.25.
Good. Yeah. What's a 0.03?
What now? Oh, it was a point. Oh,
Is it 0.01, 0.03, or is it 0.01, 0.09?
0.09.
Okay. I'm thinking of R. She's thinking of R squared. So 0.01, 0.01, 0.03, no, 0.01, 0.09, 0.25. Small, medium, large. And I would use the same, yeah, you could use the same, you could use the same calculus here. And so in our case, we still have a significant main effect for party ID, and then we have a significant interaction between the 2 independent variables after controlling for the covariates. And from this point forward, your analysis would proceed in the same way as if you weren't using the covariates, with just maybe an exception or 2 that we'll get to in just a minute. And so in our case, the next step would be to look at the interaction, right, because it's significant, and we'd interpret that first. And in most cases, once we interpret that, interpreting the main effects tend to be less meaningful because the effect of one of the independent variables is conditioned based on the value of one of your other independent variables, by definition, because you have a significant interaction. And so one thing that we do, one thing that we have, and this would be a difference that's worth your attention, although substantively it usually doesn't matter that much. But what SPSS does for us anyway is it estimates means after accounting for the covariates that you have in the analysis. And they call these estimated marginal means. And we can see in this note down here that it says covariate appearing in the model are evaluated at the following values. And these values are just the mean value. If you calculate the mean, it's just the mean value for all of the covariates. And so these are the estimated means after, and the reason why we say estimated is because we've taken into account the covariates. And so, for example, if we look at male Democrat, their mean was 3.53. If we look at male Democrat, these are unadjusted, their means are 3.56. So not a huge difference. Substantively, we wouldn't make different conclusions. based on 3.53 and 3.56, you just wouldn't say anything differently about it. But I think in practice, you should report the estimated marginal means and then reference them as such. You could, and I see a lot of people report, I don't see anybody ever report both of them. My preference would be to report the estimated marginal means because you think the covariates matter, and if that is in fact the case, we should look at means that have been adjusted as such. And so my preference would be to report the estimated means. Some people report just the straight means, the raw means without the adjustment. And so people do either or. And I think people report the raw means because they might not be quite sure what's going on here, or they don't. I'm unsure, to be honest with you, but I see a lot of people report ANOVA, and they're just reporting the raw means, and they're doing an ANCOVA, and they just report the raw means. And I would recommend if you do an ANCOVA, do the estimate means. And so just to give you the place where we got those is when I did my analysis and I did options and I said display means for. If I take that out, it will only give me these descriptive statistics, which would be the raw means. And it prints off at the top, when you did your ANOVA and you ask for descriptive statistics, it gives you the mean and the standard deviation for all of your groups and the n for all of your groups, and it prints that off towards the top of the analysis. And that's all you get. If you say display means for, that's when it calculates the marginal means. Estimate marginal means. And so in this case, we might want to do female, we might want to do male, and then I'm not going to, well, we could ask for postdoc test. It's going to give us some kind of warning message. And these would be the estimated means for the male-female group. And these would be the estimated means for the Democrat, Independent, and Republican group. And these would be where's the table that I had? Where's this table? Where's this table? I'm asking you. So here's what I'm going to do.
Is it the one at the bottom?
Here's usually what I do. I just delete everything because I've gotten a headache by this point, and then I'm just going to rerun it. Because sometimes it's hard. You end up, you're looking at the previous analysis that you did. Did somebody have a recommendation? Maybe I need to put this in there, I think. I think that'll do it. This. I'm not going to put it in there. I'm going to run it, and we'll see. And so here are the estimated means for, again, estimated based on our covariates for male and female for one of our main effects, right? And these are the estimated means for our second main effect, party ID. And then these are this doesn't help me, and this doesn't help me. And so if I delete this, I just really like to delete it. And then run it again. But this time, under options, say that I want this. This will do it. right, because I want the cross of those two. So main effect for male, female, main effect for party ID, and then this is the cross of the two, which that should look like the table that I showed you earlier. So you have to have the interaction. You have to ask for. You have to ask if you have a significant interaction, and you want to know the. You want to know the cell means, not the marginal means. You have to ask for the ask it to display estimated means for the interaction. Does that make sense? And so just picking up where we left off. We would report these means if we want to report the means. If we plot it, we would plot those means in SPSS. In fact, we plots the estimated means for us. And this graph here is just my way of showing you that there isn't that much, this is trust in the media on the y-axis. On the x-axis, it's just our different, it's male, Democrat, Independent, Republican, female, Democrat, Independent, Republican. It's just showing you that the difference between the raw and the estimated at each of these points. So this is the dotted line is the estimated mean. Well, it's not that different as we saw from the actual raw mean. And there's a little bit more difference here maybe. And the difference here is probably about the same. So there isn't in this case a large difference between the two. Substantively, you would make different conclusions. You would make different conclusions regardless of whether you used the estimated means or just the raw means, or just the unestimated, the actual means before the covariates were considered. So we'd come to the same conclusions here as we would with the one-way ANOVA or the two-way ANOVA that we did last week. We're going to stop here. There's a couple slides here that if you feel so inclined, you can take a look at in terms of if we wanted to do, let's say we did an ANCOVA and we wanted to do simple effects analysis, how would we go about doing that, right? Because we now can't use t-test, right? Because in t-test we have no way to include the covariates. So you would have to do your simple effects. You'd have to do them all with ANOVA. And actually they'd be ANCOVA. And so in our case, and the two slides that I have after this would be a way that you could use syntax and SPSS to do that analysis for you. And there I give you some cases where you might want to do that. None of those cases will be anything that we'll work with in this class, but for your future reference, possibly. So somebody, if we were going to do, let's pretend for a minute that this isn't an ANCOVA, it's just an ANOVA. How would we assess the simple effects? One of our independent variables is party ID. The other independent variable is whether they're male or female. What simple effects analysis would we do?
So if you split it by male and female to test party ID, you would run an ANOVA for that one.
Yep, and so we get two different, by doing that split, we get two different ANOVAs, right? One for male and one for female. Good. Then what else would we have to do?
Split it the opposite way and do the t-test.
Yeah, we'd split it by party ID, and we'd get 3 t-tests, one for Democrat, Independent, and Republican, and we'd be looking at the difference between males and females, right? And so that's assuming we didn't do the analysis of covariance. If we did do the analysis of covariance and we wanted to do the simple effects analysis and we didn't want to read those 2 slides that I give you on the next 2 slides and write the code in SPSS, you could do ANOVA for the t-test. So what we could do is we could split by, we'll just do it. We'd split by party ID again, and instead of doing the 3 t-test, we'd do 3 ANCOVAs. But SPSS takes care of all of the magic for us behind the scene, right? We just have to give it the right information, and it runs the analysis for us, right? And so, and then we'd essentially have the exact same. We'd have the same simple effects analysis as we did with the ANOVA, but in this case we've covaried out that set of variables that we want to covary out. So to do that, it would be we'd have to first split, right? And so we're going to do data split file. In this case, we're going to split by party ID, right? And then I'm going to do univariate, and I'm going to get rid of party ID. It would not be happy with me if I left party ID in there, because all of those groups would have 0 people in them. I don't know if it's going to error out or a warning, but it might break it for all we know. So I don't think it'll break it. But so we're just going to run this analysis. I think I also need to change a couple things over here. Oh, it automatically changed and got rid of the interaction and the main effect for party ID. And then I can run this, and what I'll have is three analysis of covariance, where I have males and females as the independent variable. And I'd be able to, again, interpret that the same way as you would interpret any other analysis of variance. And the reason why we can't do the t-test is because with t-test we can't covary. So it's a one-way ANCOVA, and our independent variable has 2 groups. And that would be a perfectly justifiable reason for using ANCOVA with an independent variable, or ANOVA framework with an independent variable that has 2 groups, is because you want to covary out some set of covariates. So I think that takes me to the end of, that was a slide deck that had like 54 slides, right? We should celebrate something. 55 slides. I don't know what we're going to celebrate. So questions on analysis of variance? Questions on analysis of covariance? We're going to get started on. So we've already done, look at us, we've already done part of our agenda, and now we're going to knock off another part, and then we'll just have MANOVA left, and it's all over. So that will be our celebration. So do I have the right due date a week from today?
Sure.
Yep. A week from today, I have the right month. Assignment 6 is due. The last assignment, right?
I thought
Yeah, you shifted that to 2 weeks from today, to the 19th. That's when we will take home exam.
we did the 12th.
What? What's the date?
I just moved. I know it got moved on the agenda.
This is, we moved the ANOVA.
Needed
To today, and the multivariate analysis to the 12th next week.
Which is,
I could have sworn it was.
This one, yeah.
It doesn't really matter to me. I have to do the same amount of work whether it's the 12th or the 19th. But
Well,
the 19th, we still have a class period in there, right?
Yes.
So the 19th,
That's when we get our take home.
I mean, what would be best for you is to do it as soon as possible after we talk about it, if I were in your shoes. Wait a couple weeks, and you might forget a couple things, right?
So due on the 12th.
Well, did I say I'm not going back if I said it's going to be due on the 19th? Which I don't know. We've never talked about this assignment before, though.
I
But
think
we
once
talked
moved
about-
the other one, we just naturally moved the other.
Yeah, we moved.
Oh. Okay.
I remember us moving the last assignment, but had nothing.
I'm
to do
good
this
with moving the
assignment.
last assignment, though. Even if some think I said that or I implied that, let's move the last assignment to the 19th. But I would encourage you to do it before then, because right. So it'll be due on the 19th. But do it before then because there's just be an extra week that will pass. I'm good with that. It doesn't. The work is all the same to me, and I think it is for you as well. So the 19th for this time, and then we have a couple weeks. So next week we'll talk. As I'm looking at the schedule, we'll talk about structural equation modeling, and then the week after we'll talk about mediating and moderating variables. We've already talked about moderating effects some because that's what an interaction is. Just another name for an interaction is a moderating effect, and so we've already covered a little bit of that. But there's a couple other frameworks we can look in, and then at the 19th would be take-home exam. You get that, and then you're also gonna, if you hadn't done it before, you're gonna turn in assignment number 6. All right. So assignment 6 is going to be a two-way MANOVA with theoretically meaningful variables and at least 3 dependent variables. And I also tell you that you need 1 or more covariates if needed. So I don't tell you have to do the covariates, but you should think about it. If there's some covariates in your analysis, because we haven't done analysis of covariance yet, and this would be a good time for you to do that, maybe a better time than if I ask you to do that later, get a little feedback on that. So I'm not saying the take-home exam will have analysis of covariance on it, but it could. And so if you have covariance, I'm happy to help you work through your data to help you determine if there's something there that you could use. And then everything else should be, 2 and 3 should be pretty routine by this point. Questions on assignment 6? When is assignment 6 due?
Ideally the 12th.
Thank you. But 19th to be technical. So let's just do a couple more slides. And as you'll see, there's only probably 12 or 10 slides total.
14.
14, wow. Does that include the one we just looked at? 13. And then the title. So we have fewer slides here than we've had for a lot of our content. One of the reasons being is because it's really just an extension of ANOVA where we have multiple dependent variables. And so what we have to do is we have this framework that we use to assess at the multivariate level, are there differences? And then if there are differences, we proceed. If there are not differences, we stop and we write up our results as nope, no differences. If there are differences, significant differences, meaningful differences, then we proceed, and we proceed to interpret a set of ANOVAs. Exactly the same ANOVAs or ANCOVAs as we did previously. We look at, so if you have 3 dependent variables in your analysis, you're going to look at 3 ANOVAs or 3 ANCOVAs. Exactly the same interpretation, exactly the same post hoc tests, exactly the same interactions. So we're only adding one small piece, and it's that as sort of that top level multivariate piece that we're adding, and then everything after that is we've already done this, and it's just going to be more review. So I don't give you the output here, but on the course website there's an HTML file. I would encourage you to download that to your computer. Those of you that have your computer open, because I'll just run the output and then we'll review that. And I didn't give you the 80 pages of output. Well, we don't get quite 80, but SPSS gives us plenty of output when we do MANOVA. And instead of adding that all to this, I just set it as a file in the course files. And so just remember, we have a two-stage process that we work with, and the first we're gonna spend most of our time here just talking about the first stage. And at this first stage, we're asking, is there a mean difference, or are there mean differences between the group and some combination of dependent variables that you'd be examining? So say you do an experimental study where you manipulate 2 independent variables and you maybe collect data on 5 dependent variables or 4 dependent variables. I see a lot of studies that look very similar to that. Manipulate 2 independent variables and you're collecting data on 5 different dependent variables. It would make sense. Many reviewers would ask you to use the MANOVA framework to do your analysis, because you do in fact have 5 dependent variables or 4 dependent variables that you're interested in assessing. And so it would be very typical, it would be atypical to look at that as 5 separate ANOVAs or 5 separate ANCOVAs. It would be much more typical to put that in the framework of MANOVA or MANCOVA and assess it using that framework. But again, after we get past the multivariate stage, you get to the exact same place you would get as if you did 5 separate ANOVAs or 5 separate MANCOVAs. It's exactly the same interpretation. Tyler?
So you run the ANOVA to see if there's a difference between these outcome groups, and then based on a statistical difference, you would analyze which independent variables have led to these identified outcomes.
Exactly. So it's sort of a 2-stage process, and if we find significant main effects or a significant main effect at the multivariate level, then we'd go on to examine that main effect at the univariate level using the same skills that we've acquired up to this point. Good question. Other questions? So again, not because it's something that we're going to do here or that we have to do, but and looking at that second point, there's behind the scenes, as I indicate there, what is happening is a new dependent variable is created, and that newly created dependent variable is what is used to examine, are there differences across your groups for this newly created dependent variable. And one of the later slides that I have, I give a few more details about this newly created variable, but it's nothing that we spend any time on in this class. But for our purposes, it's useful to just have that concept in mind, that the first step, what the MANOVA procedure is doing, is it's creating a new dependent variable that's a combination of all of my dependent variables, and it's assessing that and the differences across my groups, that is your main effects and your interactions that you have in your framework. And we examine these omnibus results, and if they're significant, we then look at each dependent variable by itself for those significant results. A couple of advantages of MANOVA. Of course, if you have multiple dependent variables, it increases the chance, for better or for worse, of finding effects. And there would be some protection against type 1 error rate inflation, particularly if you're making Bonferroni adjustments across all of the work that you're doing. So there are some advantages. Again, I think if you did an experimental study and if you had 3 or 4 or 5 dependent variables, and if you didn't do MANOVA, I would be surprised if a reviewer didn't, and the same independent variable or variables in all cases, I would be surprised if a reviewer wouldn't call you out and ask you, why didn't you use MANOVA instead of just 5 of the same ANCOVAs or ANOVAs, just changing the dependent variable each time. Of course, there's a few disadvantages. Certainly there's some additional complexity there once you sort of get through. One of the things that makes it, I think, somewhat complex is because, and this is really easy to get through or to work through and to understand, but SPSS, as it does in many situations, it gives you way more output than you need. And in many cases, well, and with MANOVA, it's even more so that you get the same results in several different places. And so because of that, it seems like it must be more complex than it's leading on to be, because there's 35 pages of results here, and there has to be something that's being missed. And that just isn't the case. It isn't particularly complex. And we'll try to look through the output and determine, well, what can you just cross out? What do you just not have to consider as you're looking at your analysis? But having said that, there is a level of complexity that's added just because we're doing this multivariate test, and so I don't want to diminish that. There are some additional assumptions that we'll go over. The outcomes can be ambiguous. Let's say you did your experimental study, you had 4 dependent variables that you collected data on. Theoretically, you should have found results across, or similar results across all 4 of those. Maybe you find results across 2 of the 4, or 3 of the 4, or 1 of the 4. And so that's what I mean by ambiguity. There might be, because you're dealing with multiple dependent variables and some chance, they're just by chance, you might have results that could be less than clear. And there's usually some power loss when compared to, so a greater chance of making type 2 error. It's probably not particularly meaningful in all cases, but it's worth consideration in especially with data where the n is small. It might be something that you'd want to take into consideration where ANOVA might be better, and it might help you to avoid making that type 2 error. So let's take a 15-minute break, and then we'll come back and work through the remainder of these slides, and then we'll do some analysis and look at that. Thank you.